Welcome to the Sophistic online documentation. This part of the tutorial focuses on the workflow-related steps for performing the Footfall analysis of floors within the Sophistic structural desktop, specifically Modal and Footfall analysis in case of self-excitation. We begin by calculating the linear load cases, the additional dead load and live load using the linear analysis task. Next, we proceed with the modal analysis using dynamic eigenmodes task. For this analysis, we assume the concrete is in a cracked state and therefore reduce both the shear and bending stiffness by 50% for groups 10 and 20 to account for reduced structural rigidity. We then convert 100% of the previously calculated additional dead load and 30% of the live load into equivalent mass. A total of 10 eigenmodes will be requested, after which we proceed with the calculation. The calculated eigenmodes can now be reviewed in the viewer. The first eigenmode has a frequency around 9 Hz, which falls into an overlapping range where both steady state and transient analysis could produce the most unfavorable results. The remaining eigenmodes exhibit frequency that steadily increase, reaching up to 25 Hz. The next step is to perform the actual Footfall analysis. This step is currently supported via Sophistic text editor input and has been implemented within the scope of the FabBench module. We begin by selecting the appropriate FabBench task to request the Footfall analysis. The analysis will use the previously calculated eigenmodes, which have been saved starting from load case number 10,001. For the type of check, we select the CCIP method. Alternatively, the SCI design guideline check is also available. Since we are unsure which method governs the performance of this floor structure, we will request both analyses, steady state and transient analysis. CCIP recommends a cutoff frequency of 15 Hz for eigenmode selection in steady state analysis. For transient analysis, all modes up to twice the first eigenfrequency must be considered. Therefore, we specify 20 Hz as the cutoff frequency for transient analysis. The results will be saved in load case number 30,000, with the transient analysis results saved in the subsequent load case. Next, we define the response locations, which are the points where response factors will be calculated. This can be done either by specifying individual finite element node numbers or by providing a group number. If the group contains quad elements, all associated nodes will be used as response locations. We will use the group-based approach. Additionally, we will assign different target response factors. Value of 8 for the hallway area within group 10 and a value of 4 for the office space within the group 20. These limits reflect acceptable vibration levels and are typically prescribed by design guidelines, depending on the area's use. In this case, a stricter limit has been chosen for the office area. We can now select the prescribed load pattern for floors, choosing the one defined in the CCIP design guide. For the excitation type, we will start with self-excitation. In this case, there is no need for the selection of explicit excitation locations. Each response node is automatically paired with itself as the excitation source. Self-excitation offers a quick and computationally efficient calculation, but may be less conservative compared to full excitation. For the steady-state analysis, we define a walking frequency range from 1 to 2.5 Hz with a frequency step of 0.01 Hz. Only the upper limit of 2.5 Hz will be used for the transient analysis. The default walker's weight has not been modified. We can now proceed with the calculation. In the next video, we'll review the analysis results using the report and the interactive graphics task. Thank you for your attention.